Okay, so what is a Bayes classifier that we mentioned earlier? What is it? Well, it depends on the problem. There is not one uh, Bayes classifier. It mostly refers to an approach where we take into account our prior belief about what the answer should be. So that's the only difference. So instead of just looking at the data, we sort of look at data and average it with what we believe the answer should be prior to seeing the data. And I will explain this using this specific, simplest example, binary classification. Okay. So we have a binary random variable y, which can take two values, 1 and 0, with probability pi 1 and pi 0, such that pi 1 plus pi 2 is 1. You can think of y as this state of an individual or of an item that we like to know, but we don't see it. What do we see? We see some other signs. For example, if we want to know whether somebody has a certain disease or not, we will, for example, do a blood test, and we measure certain things in the blood. And those will be an indicator whether y is 1 or 0. And the simplest way to model this is using a Gaussian distribution. Essentially, we're saying that, okay, let's say we are the only thing we don't see y, but we see x. X you can think of as that thing that we try to measure in blood. And if it's 0, then it will take a value according to this distribution. So it will be centered around whatever mu 0 is. You can think whatever this is, -1. And if it's 1, then it will probably have higher values of that whatever we are measuring, and it will be Gaussian. There will be some variability. The variability is Gaussian, but it will be concentrated around mu1. So higher value than a lower value. So if that disease is not present, whatever thing we are measuring will tend to be lower. Of course, it has variability. So even though the disease is not there, there is a chance that there's an individual which show a higher value of that thing that we are measuring than somebody who has the disease, because they might be at the tail of the distribution. Okay, and we want to quantify the chances of this happening. Okay, and how do we do that? Using the Bayesian formalism, which involves this binary random variable or observation x. So there's a conditional distribution. Okay. This is essentially saying that if the state is 1, the conditional distribution of x given y follows a Gaussian, the density is Gaussian with mean mu1 and variance sigma square, and otherwise it's mu0 and variance sigma square. And the Gaussian distribution, we write it in this form too. N stands for normal, mu is the mean, sigma is the standard deviation, and if z is normal 0 sigma square, that means that the mean is 0 and the variance of z, which is the expected value of z squared minus the expected value of z squared, is sigma square. Okay, so we observe x. X is along this axis. Okay, and the vertical axis here is the density. So this function is plotted, here, and this function is being plotted here. Okay, and this is x. We observe x, and we like to estimate y based on x. and we like to quantify the uncertainty about our estimate. We like to be able to say we are this much sure about what we are saying. Okay. And that's a key component of Bayesian modeling, is that it allows you to do that. And okay, so the Bayesian approach, it has a prior, it has a likelihood, it creates a posterior. Okay. Example. Okay, so this should be the other way around. This should be y, this should be x. So let me just fix that for a second. Okay. Okay. So y, the disease is present, x is test measurement. So what is pi 0 and pi 1? Pi 0 and pi 1 are the prior belief of, okay, we believe a priori that this percentage, for example, of the population, the disease is present in this percentage. It can be 99%, 95%. This is domain knowledge. This is a prior knowledge. And we want to use that to say something specific about an individual for which we have made this measurement. Okay. And essentially it boils down to, okay, you have this prior belief, you have this likelihood, which ties the observation to that unknown state that we like to say something about. And then we combine these two to get the posterior distribution. And how do we compute it? Using the Bayes rule. Probability of y given x is probability of x given y times probability of y divided by probability of x. Okay. Now, whenever you do this reversal from likelihood to posterior, you're using the Bayes rule in a way you're following the Bayesian approach. Now, there are differences between all these different Bayesian approaches is in the differences of the priors and the likelihoods and the data generating process, where the data is coming from, what is reasonable to assume as a likelihood for the data or the prior. So these things all change, and when they change, calculating this can become more difficult and easier, and then you have to do certain things. And one of the things which is not in the syllabus, but I hope I will talk about, is naive Bayes. Okay, so in this example, the probability of x is a PDF, it's a probability density function. And what I mean are these two functions, right? This is probability of x given y. X is a continuous variable, so it cannot take the probability that it will take any specific value is 0, but that's why we have a density, okay? And how do we calculate probability of x? Well, it's conditioning. You know this from Stat 2000. There are only two possibilities. Either y is 0 or y is 1. And if y is 0, then the probability that x, whatever it takes, given y is 0 is this, multiplied by the probability of y being equal to 0, and then you add it. The same thing when y is 1. And this conditional probability here is essentially a density, conditional density, and the probability of y being 0 is our prior belief. Again, before we make a measurement, what is our belief today, the percentage of individuals who have a certain, that certain disease. So when somebody takes a test, we take that into account, and this is how we take that into account. This is how we calculate probability of x, which is a PDF essentially. And note that this only will depend on x. The dependence on y is gone because y is either 0 or 1, so it does not depend on y. Now, why do we want this p of x? Because it shows up here. So we have to multiply the prior by the likelihood divided by P of x. Okay. As I said, this doesn't depend on y. This is the conditional probability. Now we want to find, this is basically the posterior probability of y given x. Okay. Y can only take two values, right? So let's calculate the posterior probability for each of them. The probability that y is equal to 0 given x is the probability of x given y being equal to 0 times the probability of y being equal to 0 divided by the probability of x. And the same thing. And obviously, if you add these two, they will add to 1 because y can only take one of these two values. Okay. Now, in Bayesian analysis, a lot of times people will write probability of y given y is, they use this sign which normally would mean alpha, but here it means proportional to y given x, x given y times probability of y. And why do they say that? Because what they care is only the dependence on y. They don't really care about, honestly, the probability itself. They typically care about finding the y which makes this the highest probability. In other words, they want to know which of these two is bigger. Like if we know that this is bigger than this, then obviously then we say, okay, we classify it as 0, and if it's otherwise, we classify it as 1. And in order to do that, we don't really need P of x because P of x is the same in both, right? P of x is the same. So that's why a lot of times people just write, they just ignore this P of x because it's a common term, and they just say P of y given x is proportional to x given y times probability of P of y. Okay. Now, putting that aside, let's just do a little bit of algebra, and we will essentially, what I will do is do this. Okay, so we have here defined what probability of y being equal to 1 and probability of y being equal to 0 is. We have the conditional densities. This is the posterior distribution. We know that P of x is the sum of these two, and then we know these two functions are Gaussians. And once we have P of x, this is pi 0, this is the conditional density. So we plug it all in to do the math. This is just algebra, you can do it. I will not spend much time on it, but I'm sure if you spend the time, you can show that probability of y given 1. Well, I suggest you do this as a homework because later we will do this in a multivariate version. Okay, but what I'm here essentially doing is I'm just substituting the value of each term. So probability of y given equal 1 given x is these two. This is the density. Now you may say, what happened to the square divided by the square root of 2 pi sigma square? Well, I leave it as a homework, but essentially it cancels out. P of y being equal to 1 is pi 1, and P of x, so if you basically cancel out if you get rid of these terms, which is common, then you will get this. And then you divide this by, take this here, you expand this, so x squared mu1 squared minus 2x mu1, and you divide it by 2 sigma squared negative. This pi 1 comes up, you get log pi 1, and then you simplify it, and this is what you get. 1 plus 1 plus e to the power of something. And that something has the only dependence on x is here. So it's x times a constant plus a constant, where the constant depends on pi 0 and pi 1 and the difference of the mu's and the sigmas, and this is how you can calculate the posterior. Okay, so now you may say, wait a second, in real life, okay, this is all a reasonable model. Great. In real life, we don't have pi 1. At best, we have an estimate, right? We have a sample in the population, and then we can get an estimate. We don't know what's the conditional distribution. Now, then what is this? Why is this useful? Well, the idea is this. Let's assume this is how the world generates data. Okay. Then, if an oracle would tell us what is mu1, mu0, sigma square, and all these pi 0 and pi 1, all these parameters, then we could just plug them in here, and then we make a measurement x from this individual, we plug it in, and then we get this probability. It will be something between 0 and 1, and if it's probably greater than something, then we would say, okay, great. So in the previous lecture, when you heard the expression optimal Bayes classifier, it meant that imagine an oracle would give you all these parameters precisely. Okay. Even in that scenario, this is as good as you can do. You can't do better than this. You can't get a precision of 100%. There will be always some uncertainty. And that's the whole point. That there is something irreducible uncertainty here that we should not even expect to reduce. And it's important to realize that that's there. Okay. Now, on top of that, this is in the best case scenario. On top of that, we don't really have this mu1, mu2, pi 1. I mean, we can estimate it from the data, and in the future, we will talk about this. But this is just an illustration of the of what we mean by an optimal Bayes classifier. And the example we used was a simple binary classification. Okay. Now the next thing would be to see if we can find some meaning here, or is this just like some mathematical formula which we are unable to get some insight or intuition from, or is it just, or is it the other way around? There is something meaningful in it, and there is, and let's look at this. Okay. First thing I want to draw your attention to is logistic regression. If you haven't seen it, that's fine. I will cover it, but if you have seen it, you recognize this formulation. Probability of y given x is beta 0 plus beta 1x. And have you ever asked yourself, where is this coming from? Like, why this form? Why not so many other forms? And I'm not saying this is the reason, but this is a nice connection. One could say that these two terms together is essentially beta 0, and mu 0 minus mu 1 divided by sigma square is beta 1. So essentially the dependence is on x is similar. The form is similar. Okay. Well, logistic regression we will cover in depth later. So, and the big question that we will learn is that if we have a data, and the data that we look at, we always describe it in this form. It's a set of n data points, and data for us, when we're talking about classification, has two components. One is x, the other one is y. Y is the label, And since we will focus heavily on binary classification, the label is 0, 1 or -1, +1, depending on how you label your categories, or 1, 2. But essentially we call it y. And then we have x, where x is a vector. I mean, even though here x in this example is not a vector, x is just one scalar, it's just one number. It's not a vector. In most examples that we will cover here, x will be a vector, meaning that it's not only one predictor. We have many predictors. And the number of predictors can be actually larger than the number of observations, but more of that later. Essentially what we want is we have the data, n data points, pairs between the independent variable, or what we may call also a feature or predictor, and the response variable or the output. And from them we want to estimate these. How do we do that? Okay. If we want to estimate the parameters of a logistic regression, what if we want to estimate pi 0, pi 1, mu 1, mu 0, sigma square from the data? These two questions, because in real life, this is the only thing we have. We don't have an oracle that tells us the truth. Okay. And even when we have it, how do we make a classification? Well, let's look at this. This is the probability of y being equal to 1 given x. Let's take some time and look at this. Okay, so we have two classes here, 0 and 1, and we want to find, we haven't yet come up with the classification. We have just come up with the probability that y is equal to 1, and what is the probability that y is equal to 0. Now, how do we go from there to a classification? You could say, well, if it's greater than 0.5, then if either probability is greater than the other one, then let's just classify it as that class, which is something reasonable. But there is something important about this to consider. This threshold 0.5 is sort of arbitrary. Why? Because it assumes that the cost of making a mistake is the same regardless of what the true label of y is. So in other words, if you have a false positive or a false negative, if you have a type 1 error or type 2 error in hypothesis testing, there are two types of error, right? Type 1 error and type 2 error. This is connected to that. And so I'm here, we picked 0.5, but I just wanted to remind you that this 0.5 is arbitrary, and if we, for whatever reason in the context, it's a domain-specific issue. If the cost of making one mistake is higher than the other one, then this threshold can go closer to 1 or closer to 0. Okay, well, let's say 0.5. So we are saying essentially that the cost of making either mistake is the same. And when will this be greater than 0.5? Well, this is 1 plus e to the power of something, right? And e to the power of something this is how it looks, and if you cross, this is 0, so e to the power of 0 is 1, so e to the power of anything slightly greater than 0 makes this greater than 1, and anything slightly less than 0 makes this less than 1. So if e to the power of z is less than 1, then z is less than 1. And if this is less than 1, then this probability is greater than 0.5. In other words, if this term is less than 1, then we have 1 divided by 1 plus something that's less than 1. So it's 1 divided by something that's less than 2. Therefore, this is greater than 0.5. So essentially, we can say that, okay, if this quantity is negative, then label this as 1. So all I said essentially means that what I was trying to say was that to have the probability of y given x greater than 0.5, the quantity in the exponent needs to be less than 0. Likewise, if it's greater than 0, then the probability of y being equal to 1 given x is less than 0.5, and then the probability of y being equal to 0 given x is greater than 0.5. Okay. So, again, if an oracle gives us mu0, mu1, sigma square, pi 0, and obviously if we have pi 0, we have also pi 1, then we can calculate the optimal Bayes classifier estimator, and we can also find these probabilities. And this is it. Okay. Now, okay. Now the next question that we will tackle will be, what does this mean? What is the meaning of this? Does it mean anything? Can we decipher some intuition? Why is pi 0 over pi 1? Why is it mu 0 over minus mu 1? Why not the other way around? And we will be able to see that this inequality, essentially, what it tells us is this. You know, again, let's come back to this figure. If the disease is not present, the measurement will be somewhere around here. If the disease is present, the measurement will be somewhere around here. And obviously, because there is variability, there is a chance that even though the disease is present, the measurement might be at the tail, left tail, and vice versa. Even though the disease is not present, the measurement might be on the upper right tail. Okay, and we want to quantify the probabilities that something like this will happen, and we want to classify this in a way so that we minimize the chances of making either mistake. And essentially what it means is, where do you draw the line here? Where do you draw the line? Do you draw it here and say, okay, anything that is to the left of this, we label it as 0, and everything that's to the right of it, we label it as 1, okay? Or you go a little bit more to the right or more to the left. And we will see that the answer to that question will depend on the prior, posterior, and yeah, basically the priors and the values of these mu0s and mu1s. Okay, and for the sake of simplicity, we can even assume that sigma is 1. So that's the next thing that we will cover. So let's look at an example, and the example is just to illustrate what's happening here, what is happening with the Bayesian. How does the prior belief change how we classify points? Okay, so let's look at this example. Let's assume the variance is 1 and the measurement, if the disease is not present, should be around -1, and if it's present, it should be around 1, and the variability is also around 1. So they have a significant overlap, and they will, exactly because they are symmetrically around 0 at -1 and 1, and the variance, they'll meet here in the middle. So normally we would say, okay, then this should be 0, should be the place where we draw the line. If you're greater than 0, then we classify you as that disease is present, and if it's below 0, we classify you as it's not present, and obviously we make a mistake, and the tail area is the probability of mistake. So then what's different here when we are doing it in a Bayesian fashion? And in order to know that, we just have to substitute these numbers. We have these ones, -1s, you plug them in here, and you get this equation. So I'm just plugging in what the values of this example are. And I picked these numbers because everything is symmetric, it's very illustrative, it's easy to see what's happening. And if you do the math, you will see that if x is greater than 1/2 log of pi 0 divided by pi 1, which is the prior proportions of not present versus present, so you can look at this as a log odds ratio, half of the log odds ratio, then label it as, assuming that the two types of errors have the same risk, label it as 0.5. Is greater than 0.5 the probability that the disease is present. Now this still depends on the prior, so let's just see how that plays a role. And there are 3 scenarios. One is that these two are equal, which is 0.5. If you plug them in, you have log of 0.5 divided by 0.5, you get 0. So if the prior says that it's equally likely for any randomly selected individual to have that disease or not to have it, so if it's 50-50, then yes, you should draw the line here. Now our intuition says that if a priori we believe that most of the population does not have that disease, that means that pi 1 is smaller than pi 0, and probably significantly smaller. So if pi 0 is greater than pi 1, then log of pi 0 divided by pi 1 is also going to be greater than 0. So this quantity will be something positive. So we'll draw it here. Draw the line here. What does that mean if you draw the line here? It means that in order for you to it essentially means that now it's harder for you to be classified as having the disease. In other words, the measurement should be much bigger. You should have a really strong signal, because a priori we believe that most people don't have it. So if most people don't have it, then there should be a stronger evidence, and stronger evidence here means larger x. And here I said y hat is equal to 1. Y hat is the prediction. So whenever we place a hat on something, that means it's a prediction. And since this probability is greater than 0.5, I just say y hat greater than 1. Now, case number 3 is the opposite. The probability of 0 is less than 1. And then this quantity, the threshold, becomes a negative number. So you will draw the line more to the left. So essentially the take-home message is this: if the prior probabilities for either cases is equal, then you draw the line in the middle. But if one is more likely than the other one, then the threshold will get further away. So for example, if not present is more likely, which is typically the case, then that means that it should be hard to be identified or classified as having the disease present. Again, this is assuming that the cost of making either mistake is the same, which is not. So maybe that cancels it, but that's a different story. Okay, so I hope that this small but comprehensive univariate example has given you a concrete sense of what it means to do to apply a Bayesian approach. And we're talking about classification, so I used the simplest classification problem. Thank you.